All right, last time we were talking about the process of assessing protein conformational stability using variable temperature CD experiments. And we had talked about the origin of the CD signal and some practical details in terms of how to calculate molar ellipticity. We then talked about two-state folding and the thermal unfolding transition that occurs with many cooperatively folded proteins as you increase the temperature. And we talked about how to fit those data. And to fit those data, we needed fraction folded, which we can get based on the equilibrium constant, and in some cases, the total peptide concentration. And we've previously derived expressions for all of those, monomer, dimer, trimer, tetramer. And then we reminded ourselves that equilibrium constant itself is temperature dependent. You have a temperature here in the denominator of this expression that's inside the exponential. But delta G itself is also temperature dependent. And remember that delta G refers to this difference in free energy between the unfolded and the folded conformations or ensembles. So we're going to describe the temperature dependence of folding free energy in a couple of different ways. Method one is a generic way, and you can use in monomer, dimer, trimer, and tetramer contexts. And we're going to express delta G as a function of temperature using what's called a Taylor series polynomial. And sometimes we won't need all the terms in this expression, other times we will. We're going to let delta G equals A plus B times T minus some reference temperature, which I guess we'll just call T0 or T naught. The temperature you choose is arbitrary, but should ideally be someplace within the thermal unfolding transition. And then we're going to add plus C times T minus T naught squared. All right, so what does A mean? Well, A is equal to delta G when T is equal to T naught. So at the reference temperature, the free energy of folding for your protein is this parameter A. And in fact, we're going to call this parameter A delta G 0 or naught, sub-zero, for the free energy at the melting temperature. B is the coefficient for this linear term in our Taylor polynomial series. And this is going to tell us how much delta G changes when we move away from the reference temperature. So if we include the B term and the A term, what we have is the equation for a line. Y equals mx plus intercept. So A is the intercept and B is the slope. As I said, the slope. The first derivative of delta G with respect to temperature when T equals T0. And then finally, and we're going to call this delta G1. The 1 subscript indicates that this is the linear term in our Taylor series polynomial, And then C is going to be equal to the second derivative of free energy with respect to temperature when T equals, well, actually 2 times C equals the second derivative of delta G with respect to temperature at the reference temperature. And these are sort of details that you don't necessarily need to know, but you will note that delta G is going to be in units of kcals per mole. By the way, our R value here, we're going to also express in units of kcals per mole. You've got to make sure whatever you do that your units for the gas constant are the same as your units for free energy. Delta G1 is going to have units of kcal per mole per Kelvin, and then delta G2 is going to have units of kcal per mole per Kelvin squared. All right. And so I suppose we might summarize and rewrite the equation at the beginning. This equation for delta G, delta G0 plus delta G1 times T minus T0, the reference temperature. Sorry guys, don't like my T. Plus delta G2 times T minus T0 squared. All right, and this is going to be our expression for delta G as a function of temperature. And we're going to set the reference temperature. And it's going to be set at some value you choose. And then in pink, I'm going to highlight the parameters that we're going to optimize. Okay. Sometimes you won't even need a delta G2 term. You could set that equal to 0. Other times you'll need it in terms of how to decide when you need it and when you don't. We'll deal with that later. All right, and so you can apply this evenly across monomer, dimer, trimer, tetramer. You could use this same expression for delta G. All right, the second method is also somewhat generic. But you do have to be careful with your choice of reference temperature. So you can use it for monomer, dimer, trimer, tetramer. And this is based on the definition that delta G is equal to the change in enthalpy minus temperature times the change in entropy. All right, so the entropy change for folding is going to be equal to disorder of the system after folding minus disorder of the system before folding. And delta S will be positive if we increase disorder, and if delta S is positive, this term minus T delta S will be negative and have a negative impact on delta G, that is making delta G more favorable. Enthalpy change is related to changes in the strength of interactions, non-covalent interactions before and after folding. So you might call this strength of interactions gained upon folding minus the strength of interactions lost. That's just a qualitative sense for what it means. Of course, you're never going to sum up all of the interactions that you can identify in a folded state and try to put a number on that. But that's conceptually what you're looking at when you look at delta H. And of course, remember that the protein is in water, so to the extent that the structure of water changes in the folded versus the unfolded state, what happens to water can be reflected in these enthalpy and entropy terms as well. All right, so we'll notice there's sort of a linear temperature dependence here. It's almost as though enthalpy is the intercept and entropy is the slope. However, enthalpy is also temperature dependent. You feel like you're going down a rabbit hole with all of these nested temperature dependent equations. One of the things that you will have learned from PChem when you take it, if you've taken it, is that constant pressure heat capacity is equal to the derivative of enthalpy with respect to temperature. And we can alter this equation and say delta Cp equals is the first derivative of delta H with respect to temperature. And if you want, you can rearrange this equation so that it says d delta H equals delta Cp dt. Then you can integrate from some reference temperature to some desired temperature, and you will get the equation delta H equals delta Cp. Let's see, delta H at this temperature minus delta H at the reference temperature equals delta Cp times T minus T0. And we can further rearrange that to look like this. Delta H is a function of temperature equals delta H at T0 plus delta Cp times T minus T0. All right. So that's delta H as a function of temperature. We're going to just erase this and replace the T0 in parentheses with just delta H0 so that you can, that's the, so you can use this expression for enthalpy. Entropy itself can have a temperature dependence. And I won't derive this one for you. I forget sort of where it comes from, but it has a similar form. Delta S equals delta S at some reference temperature plus delta Cp times, this time, the natural log of temperature divided by reference temperature. Okay, so now we'll put it all together. Delta G equals delta H0 plus delta Cp T minus T0 minus temperature times, and this will be the expression for entropy, delta S plus delta Cp times the natural log of temperature divided by reference temperature. And then we can simplify just a bit. So I'm taking the enthalpy term delta S0 times negative T and putting it here next to delta H0, and then I'm collecting all the delta CP terms in one group. So T minus T0 minus T natural log of T over T0. And we can use this as our temperature-dependent expression for delta G, where the parameters that you're going to optimize are now highlighted in pink. So you'll have an enthalpy, an entropy, and a delta CP parameter. The enthalpy will be in units of kcals per mole. Entropy will be in units of kcals per mole per Kelvin. And heat capacity will be in units of kcals per mole per Kelvin. So unlike generic expression 1, where we were just using a polynomial to approximate the variation of delta G with respect to temperature, here we're using fundamental thermodynamic principles to derive an expression for the temperature dependence of delta G. One question you might have is whether delta Cp is temperature dependent, and the answer is maybe, but the number is small enough usually that it's not particularly necessary. And it turns out that sometimes delta Cp is so small as to be negligible, in which case this term drops out and all you have is the delta H and the delta S terms, which would convert this equation into the exact same thing, sort of, as the Taylor series polynomial. All right, so finally, we're going to discuss a special case of option 2, which is for the monomer. Okay, and we've got this same expression that we've used before. For the monomer, we're going to let temperature, the reference temperature, equal the melting temperature. The melting temperature is the temperature at which for a monomer, delta G equals 0, and K equals 1, and fraction folded equals 0.5. Okay, that definition will not hold for dimer, trimer, or tetramer. It's only for the monomer that the melting temperature is the temperature at which delta G equals 0 and K equals 1 and fraction unfolded equals 0.5. For the dimer, the trimer, and the tetramer, you can, when fraction folded equals 0.5, delta G isn't necessarily 0. You can solve for the melting temperature numerically in those cases, and I'll show you how to do that later. So, remind ourselves then that delta G equals 0 equals delta H, delta G at the melting temperature equals 0 equals delta H minus Tm times delta S. Or alternatively, delta H equals Tm times delta S at the melting temperature. Or alternatively, delta H divided by T equals delta S. All right, so now, divided by Tm equals delta S0. What this basically means is if you're at the melting temperature, once you know enthalpy, you already know entropy. Okay, so let's see how this changes our expression for delta G above. We'll have delta H0 minus temperature times delta S0, which we're going to substitute in this expression, delta H0 divided by Tm, okay, plus delta Cp times temperature minus reference temperature, which is Tm, minus temperature times the natural log of temperature divided by reference temperature, which is Tm. And we can simplify this a little bit. I won't take you through the algebra if you are struggling to see it. Go ahead and try to see how to get from what I've written here to what I'm writing below. And then this term just comes down unchanged. And so for our monomer, folding, unfolding equilibrium, this is our thermodynamic expression. The nice feature of this version is that instead of having to fit an entropy point, you get to fit the melting temperature, along with enthalpy and heat capacity. So the three parameters that we're going to optimize are delta H, Tm, and delta Cp. And I'll make a note, things that I've highlighted in pink, these are parameters to optimize so that we match our data as closely as possible. Okay. And we're going to call this delta G fit. And we're going to have initial guesses for delta H naught, Tm, and delta Cp. And sometimes in the fitting process, you have to be careful as to what your initial guesses are, because sometimes there are some combinations of these numbers that'll give you answers that are not real or cause the fitting process to mess up. For the WW domain, as an example, if you start out with about minus 30 kcal per mole for delta H, if you put Tm at about 300 Kelvin, and if you put delta Cp at around 0.1 kcal per mole per Kelvin, those are generally suitable starting parameters. So based on those initial guesses, you're going to calculate a delta G fit in blue, highlighted above, and then based on that delta G fit, you can calculate a equilibrium constant. And here, what is temperature? Temperature here is your independent variable, and you're going to get that from your data. The fitted equilibrium constant is going to be the number E raised to the power of minus delta G fit that we calculated times RT. And of course, R is the universal gas constant in the units that I just talked about. 0.001987 kcals per mole, and T is temperature from your data. So given delta G, you can then calculate equilibrium constant using the equation shown. And then, depending on, we're talking about a monomer equilibrium, If we were talking about a dimer, trimer, or tetramer folding equilibrium, we would change the form of fraction folded. For the monomer, fraction folded is equilibrium constant divided by 1 plus equilibrium constant. So this expression gets plugged into both of those spots, and that allows us to calculate a fitted fraction folded. And then, using that fraction folded and the equations we talked about last time, we can calculate a fitted molar ellipticity, which is going to be equal to 1 minus fraction folded from our fit times C plus D times T. And remember, this is our unfolded baseline that we talked about last time, plus fraction folded from the fit times A plus B times T, where this is our folded baseline. And here is where your fraction fit shows up. You will just substitute this expression in for fraction fit, and you will also need to optimize C, D, A, and B. You will need initial guesses. And we can talk later about what the best initial guesses are. Let's see, maybe we'll make this purple. Finally, to do, based on our initial guesses for delta H, Tm, delta Cp, C, D, A, and B, that's 7 parameters, we'll calculate this fitted value, and then we're going to compare that fitted value to the actual value that we observe to calculate a residual. Now this is going to be molar ellipticity of the fit minus molar ellipticity from our data that we've observed. This is just going to be the difference. And of course, sometimes, based on our initial guess, that difference may be positive, sometimes it might be negative. But we want that difference to be as small as possible for each data point. And so to make that happen, we're going to define a term called sum of residuals squared. This is going to equal the sum of the fitted molar ellipticity minus the actual observed molar ellipticity at each data point squared. And we square it so that positive deviations don't cancel out negative deviations. And at this point, we're going to tell the computer to vary delta H, Tm, delta Cp, A, B, C, and D, so that the sum of the residuals squared is as small as possible. And the computer can do this. Computers are really excellent at doing this numerically. They just vary these until subsequent changes in the parameters no longer give you any additional increases or any additional decreases in sum of squared residuals. And you can use this sum of the square residuals to evaluate the final sum of the square residuals to evaluate how good your final fit is. So, so the sum of the square residuals, if it's as small as possible, that means your fitted data closely approximate your fitted molar ellipticities closely approximate your actual data. We can use this sum of the square residuals along with some information about our data to get a sense of how good our fit is. And we're going to calculate a value called r squared. R squared is going to equal 1 minus the sum of the squared, oops, don't need to write it out, sum of the square residuals divided by another term which we need to define, which is total sum of squares. And this gives you an idea of the variability of your data. So total sum of squares is equal to the sum of each data point minus the mean, the average value for all those data points squared. Okay, so you're going to take the total, you're going to take the sum of the square residuals divided by total sum of squares, and of course the total sum of squares is going to be how much variability there is in your data. Sum of square residuals should be as small as possible, and the closer it is to 0, the larger r squared is going to be. And r squared, you can basically interpret it as the percent of the variability in your data that is explained by your model. In this case, our two-state model of folding. And so in general, our high-quality fits generally have r squareds in the sort of 0.9997 range. The output of the fit is going to give you some parameter value plus or minus a calculated standard error. And I used to use an Excel spreadsheet to do this, in which case how you get standard error was important. In this case, Mathematica generates it for us, and so it's not really worth worrying about. So the output of the fit is going to be a table of values, your 3 thermodynamic parameters and your 4 baseline parameters, and they're all going to be of this form. You have some value plus or minus standard error. Okay. Now the next step is important, because we need to have a way of determining how well we know these parameter values. Okay? And so we're going to, for each data point, generate a t-statistic for the null hypothesis that the parameter, we don't actually know what it is and it's equal to 0. So the t-statistic is basically going to be the absolute value of your parameter divided by parameter minus 0, and if you're comparing it to some other number, that other number would go there, divided by the standard error for that parameter. And then Mathematica will run a t-test for you, and it actually happens as just part of the fitting process, to give you a p-value. And the p-value is, based on your t-statistic and the number of data points you have, this is the probability that the null hypothesis is true, that is, that your parameter value actually equals 0. And the p-value, if it's like 0.001, then we can reject that null hypothesis with a confidence of 99.9%. And in general, we're going to want our p-values to be around 0.001. Now, that's not what they do in social science, but in chemistry, that's what we look for. We can tolerate some higher p-values when necessary, but in general, we're going to use these p-values as an indication of whether we actually know that that parameter value is different than 0. So the p-value for delta H and Tm, those p-values are almost always very low. Delta Cp sometimes has a p-value that's high enough that we'll want to remove it from the fit. Similarly, baseline intercepts A and C are almost always statistically significant. That is, for us, statistical significance, i.e. rejection of the null hypothesis, is when p is less than or equal to 0.001. As I said, these intercept values for the unfolded and folded baseline are almost always significant, though the slopes, B and D, for the unfolded and folded baselines are sometimes not significant. And if you identify a parameter that's not significant, one of the things you can do is remove that single parameter and retry the fit and see whether and if indeed that parameter was not significant, the R-squared value will not change a lot, but the significances of the remaining parameters will get much better. Sometimes you'll have both heat capacity, B and D, as not significant, and in those cases I usually try to remove delta Cp first, and if there's evidence for it, I will, for example, if it looks like the unfolded baseline is just a horizontal line but the folded baseline is slanted, I'll remove the slope for the unfolded I got mixed up there. If it turns out, if the data look like one of the baselines is sloped but the other is horizontal, I'll remove the slope term from the one that looks like it's horizontal and retry the fit. So that in the end we have a collection of parameters that we know their value, we know their standard error, and we know with 99.9% confidence that those numbers are different from 0. Next time, I will take you through this fitting process using a Mathematica spreadsheet. But until then, wait for it. I was trying to figure out what to say. Anyway, until then, stay safe, stay healthy, and stay organic.